bit more room there. I'll just abbreviate it as W sub P that I use for person. And then I have friction here. Two to go.
Normal force between the ladder and the ground.
Which way is it acting on the ladder?
Up.
One to go.
Normal force between the wall and the ladder.
Acting which way on the ladder?
To the right.
All right, so I need subscripts here, so I'm going to go for y sub v and y sub h for vertical and horizontal. And then 2 meters away. All right. I have 3 forces acting up and 1 acting, and the 2 acting left or right. So I think I misspoke. 3 forces acting vertically, 2 forces acting horizontally. It makes sense to have a coordinate system, at least with 2 of our coordinates in this left, right, up, down. So what do you want to make positive?
Down to the right.
Down and to the right. I'm going to call the one to the right I hat, the one this way J hat. So which way is K hat going? Yep. Indicated by the X. It's into the board. Nothing to decompose. So we can go straight to, well, we get two equations here. I hat and J hat. Again, let's just make this on some planet where G is 10 meters per second squared. Just to simplify some of the math. All right, so what's my I hat equation?
Y sub h minus friction equals 0.
Okay. And my J hat equation?
The weight of the ladder plus the weight of the person minus the normal force of the ladder, or normal vertical equals 0.
We can do some substitution here. So I have y sub h minus mu s y sub v equals 0. W sub mlg plus mpg minus y sub v equals 0. So I can solve for all of my, I can solve for my two normal forces with what I have here. But finding the value of x requires the torque. So let's go ahead and let's solve what we can here. So ladder was, I said 10, and the person is 50, so this would be 600. So y sub v is equal to 600 newtons. Y sub h is equal to 0.5 times 600, which is 300 newtons. Questions to hear? All right. Let's come up with our torque equation. Now, as we mentioned before, we want to try to eliminate some of the math that we need to do. So we actually know the values of all the 5 forces here. We don't know X, but if we can eliminate some of the torque, so there are 1, 2, 3, 4 different locations I could pick for my axis of rotation, which will eliminate 2 torques. Give me one place that will eliminate 2, or when I say eliminate torques, I mean where 2 of the torques will be equal to 0.
Is that ground point?
Here?
Yeah.
Yep, that's one, because both of these would have a torque of 0 about the point where they are acting. There's one. 3 to go. There are 3 other choices. Max.
The center of the ladder.
Center of the ladder would only eliminate that one torque.
Well, couldn't he be anywhere on the ladder?
It could be. Are you claiming that let's just make them in the middle?
Yeah.
The trouble is we want to figure out what is the value of X so that it does not slip. And so we'd be incredibly lucky if that happened to be in the middle of the ladder. So we can't guarantee that. Yeah, the other 3 are not as obvious as the one where they actually physically meet. Well, I'll give you a hint. Where those 2 meet. Right there. That would eliminate WP and the torque from WP and the torque from friction. Where are the other 2?
Or friction and, wait, R, maybe?
L.
Oh.
Yep, all right. And the 4th one?
The floor and the wall.
Oh, down here?
Yeah.
That would actually only eliminate the friction, torque from friction. You were almost there.
Are we at the top of the ladder where it touches the wall?
If you pick that as the spot, then only the torque from this force gets eliminated.
Would it be like where the normals would be out in front of the ladder? Yeah, like out there.
Yep, yep. The other end of the square or rectangle. Yeah, that's the other spot. So we have 4 spots here that we could pick that will eliminate 2 torques. Now the question becomes, what is going to be the most convenient of those 4? Since X is defined based upon this spot right here, this is the one that really makes a little bit more sense than the other 3 spots. But we could, and you don't have to do that. I mean, you could pick down here, or you can pick anywhere. You're going to get the same answer in theory. If you don't make mistakes, you'll get the same answer. Put it that way. Let's see, I want some room here, so let's go ahead and, so Y sub H, this is 300 newtons. This is 600 newtons. This is 300 newtons. W sub L is 100 newtons, and the person 500 newtons.
How'd you get the 100 newtons and 500 newtons?
This is the weight of the ladder. W equals mg. The mass of the ladder is 10 kilograms.
Oh yeah, G is 10, okay.
And then we're on a mystical planet. Other questions? We haven't lost Austin yet, but we're close.
Sorry, back-to-back 14-hour shifts, past 2 days.
But physics is supposed to invigorate you.
That it does.
All right. So let's start doing our torques here. I know the total torque is 0. It is in rotational equilibrium. It is not rotating one way or the other. Matter of fact, it's static rotational equilibrium. With this as our pivot point. And so my K equation, 0 plus 0, got those taken care of. Those are the first two. WP. Again, picking this as my axis, is WP trying to rotate it positive K or negative K?
Negative.
Negative, because we said into the board was positive. So minus the torque from the person. That writing there, probably negative torque of person. I think that's probably more accurate. What about the ladder?
Same thing.
Yep. And y sub h? I hope so. I got 0, 0, negative, and negative. I better have a positive if I want to get 0. So this is the torque from the horizontal is equal to 0. All right, so let's start going through the bit by bit. We've already thought through the direction here. Since we've already thought through the direction, all I have to do is look at the magnitude of the torque, which is RF sine of the angle between them. Got to be careful here. That is the angle when you put the two vectors tail to tail. So let's just take a look at the torque due to the person. R is a vector in that direction, going up the ladder at a 37-degree angle. That's our person. The weight is a vector acting down, W sub P. The angle between them is this. It is not 37 degrees. So this becomes that distance, which is x, times the force, which I wrote down as times 500, times the sine of 127 degrees. I think somebody just said that. Okay. Negative. Minus the ladder. Well, we know the distance, that's 5 meters, times the force, which is 100 newtons, times the, it better be the same angle as we just got. And then y sub h up there, 10 meters, times 300 newtons, times the sine of what?
Minus 37.
143 degrees. Because R, in that case, R is in this direction, that's my R sub H. Y sub H is off to the right. This angle here is 37 degrees. So that must be 180 minus 37 degrees. So mathematically, sine of 37 is 0.6, this is 0.8, so that's about negative 400x minus 400 plus 1,800 equals 0. 400x equals 1,400. Obviously, I rounded off my trig functions there, and hopefully I did not get them backwards. So x is 3.5-ish.
with the ladder, and when you're trying to go up on the ladder, or like crawl on the ladder, that fair game?
You need to get to the top without tipping it over?
Is that even possible?
It is possible. I have seen it done by the person who works there, not by any person walking by. The trick in that particular case, since that's not tipping like that, that's tipping this way, at least the one I'm thinking about.
Crawling
up
it is impossible, isn't it?
As long as you maintain, you have to have a great sense of balance, as long as you maintain the sense of balance right there in the middle.
It's like walking a tightrope.
Yeah, exactly. Now, the ones I've seen been short enough that I thought, well, I could jump and just hit that spot. I don't actually have to crawl up the ladder, but I don't know if that's allowed. I'm not sure it's worth the pain that it would cause myself. All right, so anyone's worked it out, 3.5, unless I made a mistake?
Yeah.
Ish, okay. Now, suppose instead I had got, let's assume I did everything right, I had a different angle, different numbers, but I ended up with x is equal to -2 meters as my answer. What would that mean? If x is -2 meters?
You started from the top. I don't know that you started from the top and went
Oh.
to the direction.
No, not starting from the top. We're still defining x being from the bottom.
Does that mean the person can't get on the ladder without the ladder slipping?
Actually, slightly more than that. The ladder's slipping before
Oh.
the ladder's gonna slip automatically. What if we had worked it out and had x is equal to 11 meters? What would that mean?
It wouldn't,
Exactly.
because it's 10, and
Yeah, at that point, then you could throw in some, how fast can he jump on the ladder, or what's his acceleration on the ladder? Ooh, how high can he jump? He's standing at some spot on the ladder, how high can he jump, and the ladder still not slip? Yeah. I don't know which group I'm gonna subject that problem to, but. That would be a matter of if he's jumping on the ladder, then the force he's exerting on it, the normal force is not equal to its weight anymore. That's that tact. All right, any questions on the classic equilibrium problems? The nice thing about a lot of these problems is there's more than one way to approach it and still get the right answer. The downside is if you're mixing in your head two different techniques, and then that generally does not end up well. Long thin rod. So let's see, we'll make this length here 2 meters. The mass is equal to 3 kilograms. I'm shooting at it a ball of 1 kilogram putty. The putty's going to hit the bottom right here and it's going to stick to it. The question is, how high up will this thing rise? Let's make it a little bit more formal than that. If I have some angle here, some angle theta max. So what angle will it make at its maximum? So it's obviously not an equilibrium problem. So the putty's gonna hit it and stick to it. What are we talking about? What are the magic words to help guide us?
Perfectly inelastic.
Those are the ones. And what is that, besides they stick together, what physics truth are we working with?
Change in K equals 0. Or
Oh,
less than 0. Or wait, no, I don't know. I don't remember.
there's definitely a change in K. I heard you said perfectly inelastic, right? Yeah, perfectly inelastic, there's definitely a change in K.
Less than 0, right?
The change is greater than 0. Sorry, yes, the change is less than 0, I apologize, yes. But that's not gonna help us actually solve this. What's the other major principle that we're working with here?
Initial momentum equals final momentum.
That's the one. We don't know how much energy is lost, so we can't use that as a way of actually finding out any information here. But we do know momentum is conserved. However, recognize this has a pivot point here. So this is not a linear momentum problem. It's an angular momentum problem. But the principle still holds. My initial angular momentum is equal to my final angular momentum. And what is the formula for angular momentum? Yep. I initial omega initial equals I final omega final. They are vectors. The omegas are. I have two different objects here, so really it's the sum. So we have I initial rod, omega initial rod, plus I initial putty times omega initial putty equals I, well, it's one object, it now sticks to it, so I final rod and putty, omega final rod and putty. I could have just repeated what I'd written the first time with a rod term and a putty term, and recognize that omega is the same for both of them afterwards. Now what can we eliminate?
Angular momentum initial.
You stopping there?
Yeah.
It needs something more specific. Because I have two omega initials. And it's not both
Oh, for the putty.
for the rod. The rod just sitting right there. The putty actually does have an angular velocity about this point right here. So we have to figure out how do we actually find that. But this is 0 because omega initial of the rod is 0 radians per second. Oh, I do need to do some initial speed here. I haven't used, let's use 4 meters per second. For the sake of simplicity, let us assume that the putty actually hits this horizontally. It's going 4 meters per second when it hits it. I could make it more complicated. We launch the putty so that this is the peak of the path so that it's moving horizontally at that point. Or let's just cut to the chase and say the putty's traveling at 4 meters per second straight when it hits it. And, all right, so I have rotational terms here for something that's traveling in a straight line. We need to resolve that. Imagine instead that this putty that's heading straight off to the right here, imagine it's attached actually to a string, a massless string, and what I care about is at this point right here. so that when this massless string is straight down. I know that v is equal to omega r. So the angular velocity would just be its speed divided by the radius. So I got the omega piece taken care of. What is the moment of inertia of this piece of putty? Again, imagine it's attached to a string that's rotating about that central piece there. Do they have point mass in the table there? Well, I guess not. We could treat it like a sphere. Let's do it the long way. Because it sounds like you really want us to do it the long way. Let's assume it's a sphere. Radius of, let's make it small compared to that 2 meters, so let's make it 0.05 meters. So we're talking this blob of putty is about that size compared to 2 meters long.
One times 0.5 squared, 0.05 squared.
You stopping there?
Yeah.
Okay. There's more. All right, so the moment, so we have the 1/2, not 1/2, it's a sphere, solid sphere, so, correction.
2/5.
2/5.
What page is that?
What page?
Yeah. 265?
365.
Thank you.
Why can we not use this by itself? This is a formula for moment of inertia of a solid sphere.
Is it because the putty squishes whenever it hits the?
No. No.
Doesn't that assume that the axis of rotation is inside the sphere?
And where's the axis of rotation?
There.
Yeah. So what do we have to do in order to find the moment of inertia? We did it last Tuesday.
Find the center, right? Yeah, or both of them, right?
Eventually, we will need to take the rod into account. Right now, but beforehand, they're not touching each other. And so we care about just the sphere. Or did I misinterpret what you were going for, Kyle?
No.
Okay. How do you handle it when the axis of rotation is not going through the center of mass?
Do we integrate?
Only if you are a masochist.
It was not.
There's a simpler way of doing it.
It's not the parallel axis theorem, is it?
It is. It is indeed. When the axis of rotation is not through the center of mass, you need to use the parallel axis theorem. So that's the formula if a ball's rotating about some central axis, but the axis is way up here. Plus m times, in our case, we'll just, because we don't have enough letters up here, we'll call that L. We're using L already. We'll make it lowercase l. ml squared. So if I do a plug and chug here, I got 2/5 times 1 times 0.05 squared plus 1 times 2 squared. So that's 4. And this is 0.0025 times 0.4. 0.0001. Okay.
I think you might have one too many zeros. I might be wrong. 0.05
Yeah.
squared. Yeah, 0.001.
Okay, all right. So you're telling me 25 times 4 is 100 and not 10?
No. Yes.
So we get 4.001 here. Suppose I made the radius of the putty smaller. Or let's do the calculus language here. As the radius of the putty goes to 0, what does the moment of inertia head towards? In other words, just the ml squared. So if this were a point mass, then the moment of inertia is just ml squared. Which is what I was originally intending. So let's just go ahead and go with that. If I'd been thinking a little bit better, I would have made the radius even smaller. So this equation here becomes 4 times omega, which is 4 divided by 2. That's my I omega. Equals. And recognize this 4 right here, the first 4 comes from our moment of inertia right here. This 4 right here comes from the fact that I said it was going 4 meters per second. So that's equal to my IF times omega. Excuse me. So what's my moment of inertia after the collision? Actually, before we do that, any questions?